Hi. Okay, wait. Why? So a lot of things are not. Thank you. I appreciate the private. Okay, wait. I'm getting off to a funny start here. First of all, I don't know if you can hear. Good morning, everybody. Good. I don't know if you can hear me. Good afternoon, Sophia. Good afternoon. Oh, you can't. Thank you, Amy Kanina. Okay. And good afternoon, Amy Kanina. Good afternoon, Sophia. Good afternoon, Brooke. Good afternoon. Oh, okay. Good. Oh my God. It's a whole. Whoa, that's a lot. Wow. And they're on mute, which is it. Okay, wait. That's Jada. That's oh my God. Hello, hello, hello. I don't even know who everybody. Much is happening. Well, you guys are definitely back from vacation. Okay. Whoa, that's a lot. Oh my God. Wait, is that? Oh, all right. So this is like a cross generational. Okay, and you're on mute, which makes it, I guess, appropriate but interesting. Okay, hello. And he has to talk to me after break. Oh, it is after break. Okay, well that was, and so much for that. Okay, wait. So, and there are people in the waiting room, and I can't get at the waiting room. Hold on. I know there are people at the waiting room. For some reason, it's not letting me get at them. Hang on a second. Or my board, as you can tell. Hold on. And there are people I haven't said hello to, but what is going on with the waiting room? Okay, there they are. Okay. I'll get the board is asking me for a whole new sign in. So hang on. All right. This is a rocky start. There's more people in the waiting room. Okay. Oh, so that's Felicia, Alicia, Giselle. Okay. And Nick, I believe. Okay. I say, oh, Felicia. Oh, and Alicia from that class. Okay. And Giselle. Wait, Giselle. Okay. Don't try to confuse me. I know what you're doing. I mean, if I'm not mistaken, Felicia and Alicia are in the Tuesday section. Giselle is in 102, I believe. And you can hear me. Okay, okay. So I better stop saying what is it. So I'm going to start again. Good after. It's welcome back. You're almost making me feel happy to be back. Almost. I said Sophia, Brooke, Olsmael, good afternoon. Stephen, good afternoon. Me, good afternoon. Amy, I said good afternoon. Felix just caught a Mewtwo and let's go. He's very excited. Okay. David K, good afternoon. Diana, good afternoon. Chloe, good afternoon. Jaylyn, good afternoon. Oh, Sarah, good afternoon. Oh, and now I also realize this is the class. Oh, yeah, some of you I now feel like I know better from lab 2 Tuesdays ago. That was fun, actually. That was really valuable for me. I mean, some of you, and anyway, good afternoon, Ashley. And hi, Jada. And thank you, direct chat people. Thank you, direct chat person. Um, you can hear me. Okay, good afternoon, Gianna. Good afternoon, Samuel. Good afternoon, Brianna. Good afternoon, Nicholas. Oh, wait. I mean, good afternoon, Nicholas. That's not funny. Sorry, I was confusing with the other Nicholas. Yes, good afternoon, Nicholas. Right. Good afternoon, Jamalette. Good afternoon, Jasmine. You should come again. Oh, thank you. No, I really should. I hope. Oh, thank you. No, it's a scheduling difficulty, but I really would like to. And those of you who, it was great that a lot of you really participated in that. Okay. Sorry. I'm glad you reminded me too. That perfectly helps me with the material I was going to do today. I was going to do anyway, but now that you're reminding me, or I'm remembering that you are that class, it'll be even easier to talk about this material. And those of you who did participate, which was many of you in many different ways, or even if you just like said something while I was at the tables, I mean, it really helped me get to know you even better. And I was really impressed. I think you are a very impressive class. Far more impressive than I am at the moment, or that my tech is at the moment. Let me do a couple of things because the board has to be re-signed in. And also just for people that I let in late, let me just be clear. I'm going to put things in the chat. Some of you are being very nice already about what's in the chat. I appreciate it. But I'm going to put it in again just to clarify for people that just walked in. Okay. Yes. The truth is my break was, well, I'm not gonna make excuses, but I promise I have not just been on break this whole time that we've been on break. In fact, quite the reverse. It was a big job of another kind. But all right, now let me, so I don't have the exams. I'm just saying that over and over just to, not because I'm proud of it, but just to be clear and get that out of the way. We're gonna pick up with the material that you were doing in the lab. Oh, but my board is literally not even giving me internet connection. What is going on? Hold on. Hang on. Connection failed. All right, I have to all right, I'm going to reboot the board while I'm doing that. Yeah, actually, let's talk somewhat informally. I mean, it's been a while since we've been together. I hope your break was good. Feel free to put in the chat anything you want to say about your break, whether you feel like you did get a break or not. I mean, I think it was technically longer than usual, but it certainly didn't feel like a break to me. I can relate if it didn't feel like a break to you. But so let's like ease back. I know there's not that much left in the semester either, for good or for bad. But that lab that I watched you do, oh, right. I hear that direct chat person, and there's one so far. So yes, I totally hear that, and I feel your pain, believe me. I probably literally feel. In the lab that you had right before the break, which was fun for me to join, you were doing a board meeting on the Doppler effect. Now, actually, let's talk. This is what we were going to finish today. We were going to today come to the large conclusion that we're meant to come to from the Doppler effect. And then we were going to move on to something that seems totally different, but is related. Top of the afternoon. Thank you. So the rest of the semester we spend on something that seems like a departure from everything we've been doing, but in fact is not. And that is electrostatic fields, and electrostatic and electrodynamic circuits and electric current, but and magnetism. But all that stuff gets introduced now, and it can seem like a left turn from all this wave stuff we've been doing. But the purpose of the Doppler effect is to make that transition from waves to fields. I want to pause right now, whether my board comes back or not. I want to pause right now and review a little bit, or discuss a little bit, maybe informally, maybe with a lot of participation in the chat, what it was you were trying to see in the Doppler effect in the lab, big picture and small picture. So I'm going to ask you, all right, I'm going to try to say this in a way that you can take notes on until my board comes back. I'm going to start by telling you what the big picture conclusion toward which we were driving in the lab. And then I want to back up and talk about some smaller micro moments where you guys presented and had disagreements or questions and stuff like that. But here's the big picture that, again, I would encourage you to write down. With regard to the Doppler effect, on a basic level, there's 4 different fundamental cases of the Doppler effect, right? You could have receiver approaching the source. You could have the receiver moving away from the source, what we call receding, right? And I don't care what order you put these cases in, but the 4 different possibilities of the Doppler effect are receiver coming in, receiver going out, or source coming in, source coming out, right? Those are the 4 different basic cases. And the one main thing that we were trying to do in the lab, in the board meeting, and what we really want to do at one beat in this course, is we want to take 2 of those cases, 2 cases that seem similar in most ways, and compare the results from the 2 cases. For example, one main thing we were trying to get at the lab, and I honestly, I don't think this was finished, which is one reason we're going to discuss it right now. We want to look at, assuming all the numbers are the same, what frequency distinction do you get? What Doppler shift in frequency do you get when the receiver comes in toward the source, call it case 1, versus when the source comes into the receiver, call that case 3? Okay, and let me say that again. Our main goal really is to quantitatively compare the results from case 1, where the receiver approaches, versus case 3, where the source approaches. There's a very important reason to compare those two cases. We could just as easily compare the two cases where the receiver goes out and the source goes out, but it's the same idea. But I'm going to say one more thing and then pause and try to get the board going again. But when I say, and please stop me, I know it's been a long time, so it's been like a week and a half since you thought about this, and I don't think you were asked to do any work on it since then. So please, and there's no board right now, so please do stop me in the chat, like with anything about, if you just need a refresher of what the Doppler effect is, or like anything. But to remind you, when I say, the basic structure of the Doppler effect is that you have a source transmitting a wave to a receiver. Could be any kind of wave. We're tending to picture sound waves here, but could be any kind of wave. You have a source transmitting a wave to a receiver, and one of those two objects, the source or the receiver, has motion relative to the medium through which the wave propagates. In the case of sound, for example, we're picturing the medium for sound to be air. So when I say case 1, receiver approaches source, what I'm assuming is that the source is stationary relative to the air, and the receiver is moving in through the air. And when that happens, and I hope you remember this, and I think most of you were fairly clear on the following. When that happens, when either of the two objects exchanging a wave, when either of the two objects has any motion at all relative to the medium for that wave, when either of the two objects is not in the same frame of reference as the medium for the wave, then, okay, I'm going to ask you this, actually. I'm going to pause here. Then the Doppler effect occurs, right? So I'm going to say this again. I'm about to ask you a question and get answers in the chat. So, okay, so hear this. The condition for the Doppler effect, what the Doppler effect requires is that either the source or the receiver is in a different frame of reference, has a different velocity from the medium for that wave, right? That's the condition for the Doppler effect. If that condition is met, then the Doppler effect occurs. The Doppler effect occurring means that the source and the receiver of the wave get two different measurements for what aspect of the wave. Like, this is now my question for the chat. I'll repeat it, but I want to ask you, I just want to make sure we're on the same page, especially because it's been vacation and all of that. If I send you a wave and one of us is if I send you a wave, a sound wave through the air, and one of us is moving relative to the air, then we are going to disagree. We are going to get two different measurements for a certain aspect of that wave, a certain property of that wave. What I'm asking you to tell me in the chat is, what is it that we're going to disagree on? Oh, awesome. I see one thing in the direct chat. So far, there's one, and that one person is totally correct. That's awesome. So go you, one person. I'm going to wait for a couple more people in the direct chat, and I don't care if it's right or wrong, but I'm just making sure, but that's one so far. So I'll repeat the question. What aspect of, but that is awesome. That does, oh, that's two people in the chat. And they both got it right, and I'm totally psyched. And I'll also say, I do want to say also to those two people that their participation in the lab was very noticed and very appreciated. And they're not the only ones by any means, but just to say, shout out to the two people so far in the chat. I definitely noticed that they were understanding this during the lab. And they are not the only ones. But can I get one more? I'll repeat the question one more time. What is it that people disagree? What is it that the source? Oh, it was something in the. Oh, okay, no problem. So here's the question one more time. The question is when either the source or the receiver of a wave moves at a different velocity from the medium for that wave, then the source and the receiver will disagree. We'll have two different, equally legitimate, but two different measurements for a certain aspect of that wave, a certain property. What is that property or that aspect that they'll disagree on? Like what is the Doppler effect? It's a disagreement over the measurement of what? Awesome. Awesome. Another person in the chat just came in. He or she was right. Oh, two more people. Oh, a bunch of people now. Yes, 4 people. And one of them was the person who just asked me to repeat the question. So great. Yeah, that's awesome. All right. So we have like 7 people all answering correctly too, which is great. So yeah, great. Thank you. This is a good welcome back. We can all feel good about ourselves. Yeah, the disagreement is over frequency. The Doppler effect is a disagreement over frequency of the wave. And let me pause on that for a second. I'm going to try my board again in a minute. But again, maybe today's like an informal, let's like reprocess what happened in the lab. Let me repeat, or let me clarify, since this did come up in the lab. Yes, the Doppler effect is a disagreement over frequency measurements of a wave that arises from source and receiver being in 2 different reference frames, moving at 2 different velocities relative to the medium. But to be clear, that disagreement over frequencies is a relativistic thing. That is, you'll get 2 different frequency measurements. Both are correct. It's not an illusion. It's not a misperception. There was some talk of this in your board meeting and some different valid things that were said, but it's not a misperception. In other words, both frequency measurements that you get in the Doppler effect are equally correct. You could make tape recordings or iPhone recordings of both and then put the recordings next to each other after the experiment is over, and the 2 recordings will be different. In specific, I mean, if we're talking about sound, and specifically that means there'll be 2 different notes, 2 different pitches, and each one is correct in its own frame of reference, just like all velocities are correct in their own frame of reference. Okay. So what the Doppler effect is about is frequency. What you were really trying to look at, you were trying to do the math of 2 cases. And I know the math got a little, like there was disagreements in your lab. Let's be clear. Like there were some very healthy, very hearty disagreements amongst you. Now, in those disagreements in the lab, disagreements about how to do the math or what the answers were, well, then no, not everybody's right. I mean, some people were ultimately right and some people were ultimately less right. There are right answers here. And what you were trying to do in the lab was figure out the Doppler shift, the Doppler effect. You were given the frequency of the sound as measured by the source. In other words, in effect, you were given the note, the pitch that the source would hear, and then you were told, okay, the receiver is moving in at such and such speed. What frequency will the receiver hear? And that's what you were working out. And I think you ultimately got it. I think you ultimately got it right. We're going to review that in a second. But there were some clunks along the way. But yeah, to stay big picture for a moment, you were asked to get the received frequency when the receiver was moving toward the source, or maybe in your case, moving away from the source at a certain speed. We'll review that, but we want to be solid on that. We want to be solid on that because the real goal is then to do the exact same problem again with the exact same numbers, but see what happens when the source moves rather than the receiver moves, and compare the 2 findings. Let me just, so That's the important thing. Again, please try to make a note of that in your notes or something, that our real interest in the Doppler effect is to compare the Doppler findings from case 1 to case 3, from receiver approach to source approach, or receiver recede to source recede. That's our real interest. Let me see if I can get the board back working again. Bear with me for a second, please. Okay. Okay. Good signs of okay, that's a good sign. Okay. 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 Okay, so this is today. So welcome to today. Welcome back, everybody. Okay. I would love if you know what would really help us all, I think, if you could take out, if any of or all of you can take out the stuff that you were doing in the lab board meeting two Tuesdays ago. I'd love to use the exact numbers that you were in the board meeting so I can fly through and sort of make comments on what you've, because I'd like to use those numbers. So if you could take out, if any of you could take out what you were doing. I'll write in what I know, but you're going to tell me numbers in a second that I don't remember. This is what I remember. What you were given, so that, again, please take out your things from the board meeting. You're going to fill in the numbers for me in a moment. I don't mean the right answers. I just mean the actual given numbers. You had a car, which I'm just depicting as a speaker right now, making sound, and the sound was coming out at 340 meters per second relative to the medium, right? The speed, the velocity of the wave relative to the medium, relative to air, was 340 meters per second. That much was a given. The frequency of the wave relative to the source was also given. I don't remember it offhand. I have a guess that it was either 44 or 50. I'm sorry. I have a guess that it was either like, I have a guess that it was like 500 hertz or 600 hertz, but I honestly don't remember. If one of you. Thank you very much, direct chat person. Awesome. Okay. Okay. And then you, that's helpful. And that shows you're paying attention. Then you were given one other thing, right? Or at least in one case, I think the case you were doing, now correct me. Well, I want to do the case you were doing that when I was with you. I believe the case you were doing, you were told that the source was stationary with respect to the air, but that you, the receiver, the listener, that you were moving through the air at a certain speed, which I believe was 44 meters per second. Please tell me in the chat. But also, what I don't remember offhand that I want to be consistent on is: were you moving toward the car that was blaring the horn, or were you moving away from it? Could someone, and maybe a different person, could someone tell me in the chat, please? Like from your lab board meeting, were you moving toward the sound that you were hearing, or away from the sound? Or you could use your voice too, but hello, everybody, welcome back. One person is helping me, but I want to have more than one person. I'm talking about the lab board meeting that I visited you last Tuesday. Could you, I'm not asking you to figure out answers. Just tell me what the givens were of the problem that you solved in front of me. Was the receiver moving toward, remember it says like a car blares a horn and then you are listening to the horn. Are you moving toward the horn or away from the horn while you're listening? Thank you. Awesome direct chat person. Okay. And I also noticed that was a different direct chat person, so I totally appreciate it. Okay. Moving away from the horn. That's what okay. And was it at 44 meters per second? Does that sound right? Could someone confirm? Yeah. Okay, great. Now people are talking. Okay. Phew. Oh, and I really do notice that each time in the direct chat, it's like a different person. That is really awesome. Oh, another different person. Okay, great. Okay. So here's how I notate. Now, again, I'm on purpose right now. I'm going to review exactly what you did in front of me. I'm going to show you, and I know I know Professor Walters also did it. I'm going to do it my way, and I would appreciate it if you take notes because I even have comments about you. Some of you asked her questions about her way, and I remember them. I want to address them right now. So please, we're doing this again for, in effect, you could say a third time. But then I'm also doing it to compare to the other case, which is the real important thing of all this. It's all about a comparison. So what I believe the givens are, according to what you just told me, is this. Oops, sorry. And stop me if this doesn't make sense. But here's my drawing, and I'm going to add one really important thing to this drawing in a second. Like, there's no negative signs yet in my drawing. A relative, oh, very good, direct chat person who wrote relative to air. Very good. This is my drawing. Like, it's supposed to depict, like, these are like those stupid wind things that I never draw well. It's supposed to depict that an ear is moving through the air away from speaker. The speaker is in the car. The sound is emanating from the speaker, moving toward the ear. So the one thing I'm going to do before going any further, and this is a correction, this is different from what you guys did in the lab. I'm going to analyze this. Our big goal here in any Doppler effect problem, our big goal is to solve for what is the frequency of the wave relative to the receiver. That's always the goal of the Doppler effect. What's given is the frequency of the wave relative to the source. What's also given is the velocity of the wave relative to the medium. What's also given is the velocity of the receiver relative to the medium, and all that's written here. But what you're trying to figure out is, given all that, what frequency is measured by the receiver. Now, there's no negative signs in my givens yet. There usually aren't negative signs in the givens. The givens are just raw magnitudes. But two pieces of advice I want to give you that's a little different from the way you ended up landing on it in the lab is, number one, what I would always do in any Doppler effect is, once I'm drawing my diagram, like step one DFP, once I'm drawing my diagram, I would make a coordinate system decision. I would say, whichever direction the wave is traveling, i.e. from source to receiver, the relevant direction that the wave is traveling from source to receiver, I would designate that as positive before I do anything else. And I'm telling you right now, actually, that is not what you guys did in the lab. What you guys did in the lab was tacitly, you made that negative. That is not wrong. That's what I'm here to say. What you got a lot of negative signs in the way that you did it in the lab. It's not wrong. You still could end up with correct magnitudes, but you might remember that the way you solved this in the lab, you ended up with with a wavelength. You got answers for wavelengths that were negative, I believe. It might have also been frequencies, but I'm pretty sure you got numbers for wavelengths as you were going that were negative. And one of you, I think it was Sarah, but I'm not sure. One of you literally, and it might have been Ashley. somebody at that table, somebody, and may have been, and many of you may have been wondering this. One of you raised your hand and said, hang on. And you asked Professor Walters, like, hang on, what does it mean that we're getting like negative wavelengths? Isn't that like an issue? And you were very right to observe that. I mean, believe me, I took a lot of mental notes during that day. And then so that you know also, I went straight from that, not straight, but I spent the evening at the Walters' apartment. And most of, besides playing Pokemon, mostly what we talked about was that lab period. Like we sliced and diced many micro moments, all to your credit. But I just don't want you to think that like your life is meaningless or wasted. And so one thing was that you got negative signs for wavelengths, and you correctly noticed that that's a little odd. Like strictly speaking, that doesn't really make sense. What does it mean to have a negative length? And Professor Walters' answer was right. You were getting those. It wasn't wrong based on the way you were doing it. It made sense that you were getting negative signs because tacitly, the coordinate system that you chose was a coordinate system in which the direction of the wave was negative. If you look back in your notes, you'll see that. I'm not saying but the way you set up your negative signs, it meant that the wave was traveling in a negative direction. That's not wrong, but that's a little weird. I mean, it ends up causing some confusion because then, 1 second, sorry. Okay, because then the distance from or the displacement from any one crest to the next crest, if you're tracking the wave against the direction it's going, then the displacements from one crest to the next are technically negative. So you technically got a negative wavelength. Not wrong, but confusing. And definitely right that you noticed that and you were thrown by it. So but also I want to say, I was very happy that Professor Walters went with your coordinate system. I mean, this is relativity. Anything should work as long as we consistently stay in it. It's just that some are more convenient than others. So, and again, so this is it happened that you guys set things up so that you were getting these negative signs, and Professor Walters did, I believe, the correct physics teacher thing, which is go with your mindset and see where it takes you. And it did get you correct numbers, but it was confusing. And maybe some of you were confused for that reason. It didn't anyway. So my first piece of advice, whenever you're doing a Doppler effect problem, is choose a coordinate. Just say that anything that is going in the same direction as the wave, that's positive. So that to be strictly, so here in this coordinate, and this would all go into, well, whatever. Yeah, so, and this is why I'd have it right. So I'm about to go on, but so I would say in this coordinate system for this case, oh, wait, sorry. Sorry. So in this case, when the receiver is going away from the wave, when the receiver, is running away from the source, that means the receiver is going in the same direction as the wave. So the velocity of the receiver relative to the medium is in fact positive. And I think that's exactly I think you guys made it negative, and I could see why you did, because it seemed like the way you were drawing it, I could see why you did that. But if you start by assigning your negative signs and positive signs according to the wave and then follow from there, it's in any case you do, your life will be easier. Okay, so we have that. Now, also notice the way I'm setting up this diagram. This also came up. You guys asked Professor Walters about this. You could do the way she's doing it makes total sense. And honestly, I did it exactly the same way she did it for years. But I will also say that those of you who brought up, what I'm trying to say is she only had one subscript on the frequency and wavelength measurements. Like she would write like FS equals 500. And one of you brought up like, wait, couldn't there be another subscript on the F? Or like, I don't understand, like F, like, And her point, in effect, was, well, whenever you're talking about frequencies or wavelengths, it's understood that that could only apply to waves. So the first subscript of any of those things like frequency or wavelength, the first subscript is always tacitly a W. It's always a wave. We don't have to say it because we know it could only be the wave. And she's right. And I used to do it that way too. But I also understand what you guys are coming from, that just to make this all consistent and clean and clear and easy to follow, one big consistent method, it's easy to follow. Oh, and she also said, I'm sorry, she also said, velocities are the things that are ultimately relative, according to Galileo. So it's velocities that have two subscripts. So that's all these two subscripts things came from the Galilean principle of relativity originally. So it's velocities that we strenuously put two subscripts on. And that's also right that she said that. But I'm with you, those of you who would like to see two subscripts on all of the pieces of notation in this, just because it makes the whole thing sort of easier to look at. I'm with you. That's the way I do it at this point in my life as well. So you'll notice, so this is comment number 2 about the way the lab was done, or the way you solved this problem. You could do it either way. You can totally do it either way, but I too, it makes it easier for me to see if I put two subscripts on everything. So all the velocities have two subscripts, like it's either receiver to medium or medium to receiver or blah, blah. And all the frequencies and wavelengths have two subscripts too. It's just that their first subscript is always a W for wave. Okay, so that's comment number 2. All right, I'll even put this too. Okay. Oh, there's things in the chat. I'm sorry. Hang on one second. Yeah. Okay. Yeah. Oh, thank you, direct chat. There's one person in direct chat about the two subscripts. Yes. No, I appreciate, and I appreciate the feedback. Right. There. And look, and this is the thing about board meetings. I love board meetings, and I love doing them. I love watching them in action. They're always much more frustrating to experience than, I mean, they're frustrating to experience, and you don't feel like you're learning when you do a board, especially the way you're used to learning in science. People don't feel like they're learning in a board meeting because things are confusing and they don't know whether things are right or wrong or this or that, which is why the ideal board meeting is kind of like that, like that we can straighten out all the stuff afterwards. But if I just told you all, I mean, let's note for the record, guys, by the way, you did that whole board meeting after we had done one example, I believe. Yeah, we had done one fast example of the Doppler effect in lecture right before that, just one, and I did it fast. But I did do it my way. But of course, it doesn't land if I just do it. No, it doesn't mean anything. It only now I mean, in other words, I did two subscripts in all of this, but it doesn't mean anything until everybody like does the experiment together and discovers it all together, blah, blah. So now the ideal is you did all the discovery. There may have been frustration and confusion while it was happening. You might not have known what exactly was right. I totally appreciate that. And I'm glad that I was there to see it. So now here, yes, I agree with you, direct chat person. For me, two subscripts is definitely easier. Yeah, it's clearer for me too. Okay. So now we have this set up. Now remember the goal of any Doppler effect problem, we've already said this, but of any Doppler problem, the goal is to solve for the frequency of the wave relative to the receiver, right? Again, the given is the frequency of the wave relative to the source, and what's also and various velocities, and we know necessarily that the frequency of the wave relative to the receiver is not going to equal the frequency of the wave relative to the source. Like that's the point of the Doppler effect, that they won't be equal. We're solving for the new one. We also know, and this is something you guys brought up very well, and so did she, we also know in this case, hello. In this case, the receiver is receding, right? That means going away from the source. It means traveling in the same direction as the wave. So in this case, and this was interesting, you guys had kind of an argument back and forth. And I definitely remember this. This was you really being physicists. You guys realized, many of you realized from the start that in this case, if the receiver is moving away from the source, then qualitatively, the frequency of according to the receiver, you realize should be smaller than the frequency of the wave as measured by the source. Smaller. Totally lying. I mean, bigger. Sorry. No, yeah, smaller. No, sorry. Like qualitatively. And remember, then there was a point at which you got answers. And then some of you were like, wait, those answers, like, I see the math. Like, this was my favorite thing that happens in a board meeting. And it definitely happened with you guys. Like, you had a qualitative picture, some of you, then you did some math. And then some of you were like, I see the math, but I have this qualitative picture in my head, and like, they're not matching up. And of course, this is also where the pictures came in. Like, the pictures should have helped that, but the pictures were kind of bad pictures. So you had to discuss that, whatever. But qualitatively, you are right to think if you're shouting at me and I'm running away from you while you're shouting, you just switch the view of the screen so I can say this. Yeah, if you're shouting at me and I'm running away from you while you're shouting, I do expect to hear a sound frequency that's lower than the one that you hear, for precisely the same reason that if I were at Coney Island and there were water waves coming at me from some ship that was sending them out 3 waves per minute, if I stand there on the beach, if a boat is sending out 3 wave crests per minute, if I stand there on the beach, I would expect to receive exactly 3 wave crests per minute. But if I'm running away from them while they're coming, right, they're being sent out at 3 waves per minute, but I'm running away. So as each one's coming to me, I'm making it harder for it to get to me. The amount of time between each next wave crest would decrease because I'm not waiting for them. I'm delaying the time by running away. And that's absolutely qualitatively, and stop me in the chat if you don't buy that. But I think most of you were saying that if you're running away from the source, the number we should get for the received frequency had better be a number that's less than 500 or whatever was given at the source. So now we do the math, and the math better jive with that. Right? Okay. So now the math procedure is always the same for all cases. If you really understand this math procedure, once you get it under your belt, if you're doing it right, it's not plugging into an obscure formula from the web. If you're doing it right, it's a procedure that would work for all cases and where you would not have to make any arbitrary decisions to apply this to each case. So the procedure all right, step 1, and you did this in the lab. And again, this is the thing that people would never do if they I know there's equations on well, it doesn't matter. This is a step that you do. You solve for the wavelength according to the source. And this is what you did in the lab. I'm going to do it. Notice what you did in the lab. What you're doing for each of these steps is you're applying the relativistic character of velocity to the motion of a wave, right? You're using two equations. Every time you do these problems, you're doing two equations, one that acknowledges that this is a wave, and the other that acknowledges how velocities work in general, right? So every time, and that's really like both relativity and waves. So every time when you do step one and you solve for the wavelength of the wave according to the source, you're going to say that is the velocity of the wave according to the source over the frequency of the wave according to the source. Again, this is where, yes, to me, I like having two subscripts. Also, by the way, I'm calling this stoop one. I'm being a little bit silly, but I'm saying to all of you, to do any Doppler effect problem, there's 3 specific steps we do every time. However, we already have a 5-step problem-solving procedure in general for problems, right? So these are mini steps. They're like steps outside the 5 realm thing. So I'm calling them stoops. I'm just being silly, but to be not silly, like if you were doing this on exam or something like that, these 3 steps that you do every time, I think they're all in the context of step 3 and 4 of the larger problem solving material. I don't know how to say that better, but like you do 5 steps to solve all math and physics problems. If the problem happens to be a Doppler effect, it has this specific procedure involved. So I would embed this procedure in steps 3 and 4 of the larger problem solving procedure. So I'm calling these stoops instead of steps. That's the silly part, but call them whatever you want. All right, but here we go. The wavelength of the wave according to the source is the velocity of the wave according to the source over the frequency of the wave according to the source. This is what you did in lab, but then you say, aha, the velocity, and stop me now. I'm going to say this sort of quickly because I feel like this part you've done many times, but it is the key part. You say, aha, the velocity of the wave according to the source is not known. That was not explicitly given. If I'm being careful about subscripts and careful about relativity, then I don't know what the velocity of the wave according to the source was. What I know is that the velocity of the wave according to the source must equal the velocity of the wave according to the medium. That was given. That's what we always know about waves, plus the velocity of the medium according to the source, right? Please make sure you understand that step. I do it every time, even when zeros are involved. So I do that, and then I say, oh, what is the velocity of the medium according to the source? Do we know that? Well, we know we weren't given that either. We were given the velocity of the source relative to the medium, right? And what we want is the opposite of that. Now it happens that in this case, that was 0. So we can say, okay, the velocity of the wave according to the source equals the velocity of the wave according to the medium plus 0 in this stoop, in this step, in this case, right? And that means it's 340 meters per second plus 0. Okay, so the velocity of the wave according to the source is 340. It's not always, okay, you get what I'm, stop me if you don't get what I'm saying, but that, so now therefore, the wavelength of the wave according to the source equals 340 meters per second over, I'll include the step. Right? This now, and again, I believe you got this. I believe you got a negative sign when you did it, this part in the lab, and I believe there was discussion about this, but This is stoop A or stoop 1. The wavelength of the source is equal to 0.68 meters. Now that we always have to get that first. Why? Because we go to step B, we always say, okay, or stoop B if you like. I always just say the wavelength of the wave according to the receiver is equal to the wavelength of the wave according to the source. Always. This came up in your discussion. I want to verify, and many of you said something very right about this. I want to confirm that you were right. Like our thing here is that the source and the receiver of a wave will disagree on frequency ultimately. Ultimately, because they're disagreeing on velocity. And velocity equals wavelength times frequency, or speed equals wavelength times frequency. Because they disagree on speed, they will disagree on frequency, assuming they don't disagree on wavelength. Like V equals lambda F. If you change V, you change F, but only assuming you don't also change lambda. And I'm here to assert that's right. We don't also change lambda. Lambda is the one thing that the source and the receiver agree on. No matter how far apart the two crests are to the source, they will be exactly that far apart to the receiver, no matter how fast either one of them is going. I wanted to say that one more time, because if you're really following what I'm doing, now that this is like the third time we're doing this, if you're really following this, you might realize that when we go to the other case, which we better today, yes, when we go to the other case, we're going to get different answers for the wavelength. So be careful and be aware. I am not saying that the wavelength answers are the same across all cases. They are not, and that makes a huge difference in our answers. The wavelength answers are not the same in all cases. That's why you have to solve for wavelength first. But what it is that within a case, the wavelength is the same for source and receiver. And that's the other reason we solve for it first, because whatever we get for its value, according to the source, we know we can rely on to be also the value for the receiver within a given case, not across cases, within a given case. So step B is I'm just saying, okay, whatever I just got from the wavelength, according to the source, that's going to be the wavelength according to the receiver. So now I go to, that's all I have to say for stoop B. It's that simple. Just wavelength is constant. Okay. So now I go over to stoop C, mini step, whatever you want to call it. Stoop C. It's ridiculous that I'm calling it stoop. Actually, that's definitely going to confuse people, but hold on, I'm just seeing. Yeah. Okay. So that was stoop B. Stoop C. But this 3 stoop procedure I'm giving you is the same for all Doppler effects problems. And that's the key. All right, so stoop C. So now we do stoop C given the wavelength according to the receiver. We now solve for the ultimate final thing. We solve for the frequency of the wave according to the receiver. We do it by doing the exact same procedure we did in stoop A. We say, okay, frequency of wave according to receiver equals velocity of wave according to receiver over wavelength of wave according to receiver, right? Which we now have. But then we say, oh, the velocity of the wave according to the receiver, we don't know. It wasn't explicitly given. What we know, we do the relativity thing again. VWR equals, by definition, VWM plus VMR, right? And then we say, oh, VMR, nobody ever gave us that. No one ever told us what the velocity of the medium according to the receiver is, but they did tell us what the velocity of the receiver according to the medium was, right? So that will equal, in this case, negative 44 meters per second. I believe in the way that you did it in the lab, I think you got negative times a negative, which is a positive, and all of that is consistent, but I think it was a lot of negative signs going on. So it's negative 44 meters per second. And again, oh, I meant to do that in a different color, but sorry. So now I go the other side. So I say, okay, so V wave according to the receiver equals V wave according to the medium plus V medium according to the receiver. So that's 340 meters per second plus a negative, minus, well, yeah, all right, let's say plus negative 44 meters per second. So we get 296 meters per second is VWR. So now the final answer we're looking for, the final frequency of the wave according to the receiver, is VWR over lambda WR. So that's 296 meters per second over 0.68. I guess I technically should say 0.680 meters. I'm just going to fix that on the other page. I'm just keeping things to 3 significant, just to make Professor Sheehan happy, which is important. Okay. Now wait, I've got to look at the time. Okay. So okay. Now we have 15 more minutes. Let me say, first of all, I think this is the answer we get. I think this is the answer you got essentially, although again, I think there was negative signs involved in the way. Stop me if this is not the answer you got, or if you don't understand this, but I'm going to go on in a second. But this, to me, this is just a clean review of what you did in your lab board meeting. This is the frequency of the wave according to the receiver. If the receiver is running away from the source, while the source is sitting still in the air. And notice, as you pointed out in the lab, the frequency received is lower than the frequency sent, so to speak. The source measured 500 hertz, and the receiver measured 435 hertz, a lower note, like to the left on a piano keyboard. Okay, that's the answer. Stop me if there are questions. Do put them in the chat, but I think that's the answer. Now, here's where I want to, someone's here. Okay. Here's where I want to move on. And I don't think you got to this in the lab, but this is the real point. If we go okay, we're going to keep all the numerical values the same, and we're just going to flip the case now. So the receiver is sitting still in the air, and the source is moving back at 440. I'm just going to quickly draw it again, but I'm going to say now, the purpose, if this were a lab, like this is now lecture, and we only have 14 minutes, so I'm going to, skip the drama or try to skip the drama. But I do want to say, in fact, I want you to write down while I'm making this picture. Okay, you should really, in the lab, you're supposed to do this. You should really make a note before we do the math. Predict to yourself, if we're keeping all the numbers the same, but instead of moving the receiver back this way, we're moving the source back this way. And remember, this whole effect is driven by relativity as it applies to waves, right? So we're switching the frame of reference here. Like I keep saying, instead of the receiver moving back away from the source, we're now having the source move away from the receiver. So I will tell you, I'm not trying to trick you because we only have 12 minutes, but I will tell you that certainly if I think I understand relativity, and if I'm knowing relativity is driving this whole phenomenon, I would be very liable to predict. I'd be very likely to predict that I should get that the source frequency here won't be 500 again. There will be a Doppler effect again for sure, but I would predict that the received frequency, while it won't be 500, I would think that it would be exactly what we got in the other problem, 435 or something, because it seems like we're just shifting our frame of reference if we make this new case, right? That I would put down as my prediction, I think we're going to get the same answer as we did before. Now, I'm not saying that you should I don't know what your prediction is. I'm just admitting to you that that would be my prediction. If I'm, and I'm also admitting to you that if that is your prediction, I think it's a very reasonable one that we should get the same answer as before. But I don't know if it's right until I do the math. So now with 11 minutes left, I'm going to do the math. I'm going to do if I really trust and understand this whole Doppler effect procedure, I should be able to do the exact same procedure and just apply to this case. And I should be able to do it a little bit quicker, right? So here we go. I'm going to do, so stoop A, I'm going to get the wavelength of the wave according to the source by getting the wavelength, by getting the velocity of the wave according to the source over the frequency of the wave according to the source. I'm going to say that the velocity of the wave according to the source is velocity of the wave according to the medium plus velocity of the medium according to the source. And that's all over the wave, right? And now the velocity of the wave according to the medium is 340. The velocity of the medium according to the source. Now it's not zero this time. Notice in the other case, in the first stoop, we got a 0 in the numerator. And then we went through and we didn't have a 0 in the numerator on the last stoop. Like if you really are paying attention to what we're doing, you'll notice we're doing the exact same two equations 2 times, just in the opposite order. You'd think that we would just, like first we're using velocity to get wavelength, and then we're using that wavelength to get frequency. In the other case, wait, I'm not going to repeat all this. The point is, we do the exact same equations 2 times. In one case, we get a 0 in one of the times we do the equation, but not the other. And here, we're going to get a 0 in a different place in the procedure. That's what makes all the difference. In other words, this VMS is not 0. The velocity of the medium, according to the source now, is something. Well, I look at my diagram. If this is positive, if that direction is positive, then the velocity of the source relative to the medium is negative. The velocity of the source relative to the medium in this case is negative because it's going against the direction of the wave or opposite to it. So the velocity of the medium according to the source is the negative of the source relative to the medium. So it's negative 44, right? I'm doing this fast, but if you just follow the exact same reference frame that we set up before, it'll make the decisions for you. So I say it's 340 plus 44 all over the frequency of 500, right? So 384 over 500. So we get so here, note this. I just solved for the wavelength of the wave according to the source by the exact same procedure as before, but this time I didn't get 0.68. I got a longer wavelength. because now the source is running away while it's making these waves. So it spits out a wave and then it runs away and then it spits out another. So they're longer. They're an extended wave. That's what some of the pictures were trying to show, that when the source, excuse me, is moving, the wavelength gets affected right from the get-go. Then you say, wait, but I thought the wavelength's always supposed to be the same. Right. Stoop B says the wavelength of the wave according to the source must be the wavelength of the wave according to the receiver. Those must be the same, not the same as the other case, but the same as each other. So if we now go to Stoop C with 9 minutes left, we say, okay, so let's get the frequency of the wave according to the receiver, which is the velocity of the wave according to the receiver over the wavelength of the wave according to the receiver. So now we're going to use this 0.68 as 0.768 as the wavelength. The velocity of the wave according to the receiver is VWM plus VMR. Now in this case, VMR, to cut to the chase, that is 0. The receiver is not doing anything in the air. The air is not doing anything past the receiver. So we can literally say now, we could say frequency of wave according to receiver equals 340 meters per second all over 0.768 meters. And that okay, I'm just checking one more time. All right, we have like 2 minutes left. We have 3. Okay. Okay, we have 5 minutes left. All right, that's perfect. Here's my point, a couple points. Number one, I did that a little bit. The procedure I just did, you notice I'm applying the exact same way to each of the 4 cases. You should be able to do any case with this procedure. Notice there's trickiness with regard to negative signs, but you never have to make an arbitrary choice or a memorized choice about negative signs if you follow the logic that negative just always means anything that's going against the wave. Now, if you follow those procedures, we just got 2 different frequencies for these 2 different cases. They're not vastly different, but they are different by an amount that is more than just rounding would incorporate. I was actually sort of careful and kept everything to 3 significant digits. If we had gotten 2 numbers like 443 and 442 or 444, that maybe would be rounding, but it's 443 and 435. That's not rounding. If you really wanted to test whether it was rounding, go back to the original speed of one of the objects, the 44 meters per second, and try and make that number much bigger, and you'll see a much more dramatic effect, like one that is indisputably not a matter of rounding. So what I'm saying here is if you follow this procedure carefully now, you will see not only is there a Doppler effect where the source and the receiver of a wave, if they're in 2 different reference frames, they won't just measure 2 different velocities of that wave. They'll measure 2 different frequencies of that wave. That's the principle of the Doppler effect. But what I'm really trying to tell you now is even though that's driven by relativity, if one moves like this, that does not yield the same result as the other moving like that. And if you really take relativity seriously, that's almost maybe a surprise. Like, sun moving away from Earth is the same effect as Earth moving away from the sun. That's the point of relativity. It doesn't make a difference whose perspective you look at it from. So what's going on here? what's going on, if you write this in, what's going on is relativity is definitely still absolutely self-consistent here. Sun moving away from Earth is the same thing as Earth moving away from sun. But the reason that source moving away from receiver is not the same thing as receiver moving away from source is because that's a false description of the phenomenon. The phenomenon is source moving away from medium versus receiver moving away from medium. In other words, the relativity here is that source away from medium is the same effect as medium away from source. We can say VSM equals negative of VMS. And, or we could say receiver moving away from medium is the same effect as medium moving away from receiver. VMR equals V negative of VRM. The relativistic symmetry is between the receiver and the air and the receiver, or the source and the air and the source. The air, the medium, is a legitimate and unavoidable, crucial reference frame in this whole problem. Long story short, what we're saying is relativity, when it's applied to waves, means the relativity as applied to source, receiver, and medium. The medium is playing a kinematic role in this phenomenon. What this is showing, the fact that the source moving away does not yield the same result as the receiver moving away shows that the medium is real. The medium is as legitimate an object or perspective as the speaker or the car or the person. The point of this, and I know I'm done, but I just want to drum into you, the takeaway from looking at the Doppler effect is that the medium is not just an abstract concept in our minds. The medium is a player on the stage of motion. The medium's frame of reference is as important, if not more important, as any other frame of reference once waves are involved. You cannot have a wave motion without its medium playing a crucial role in the relativity of motion. That's the point. Okay, but that is the end of class. So I'll see you Wednesday. Thank you for coming back and welcome back. And thank you for being so patient. And I'll get the exams to you soon. I don't think I'm going to get them Wednesday, but okay. Sorry. Okay. Have a good day. Yes. Have a great day.
Have a great day, Professor.
Have a great day.
Have a good day, Professor.
Have a good day. Thank you. You guys have a great day. Goodbye.